All right, well, welcome everyone. We're going to give everyone a few more minutes to join the webinar here, but this will be our ClearCalcs webinar on the Australian and New Zealand Standard 1170.2 on wind assessment for residential projects. We'll be sharing a poll that we would love for you all to answer as well. We are interested in using some of your expertise, as you all are on our webinar, to help with our future feature development. So right now, we do not currently have snow or earthquake calculators in ClearCalcs. We have a question for you of how often you do those calculations, how much they matter to you.
I'm just having a bit of technical difficulty here, Brooks, to launch the poll. Let me just
no worries.
make that happen.
For everyone who's just joining, we're just going to give participants a couple more minutes to join and then get started. But in the meantime, we'll have a poll for you, and we'd love to hear a bit more about you.
All right, I'm just going to do a pivot. So since we can't run the poll, if you could just drop in the chat to share with us, how often do you calculate snow or earthquake loads in your project? Just let us know whether that is once per year, once a month, or you never do calculate snow or earthquake loads in your project. We would love to know.
And we're trying to understand, we have our wind load calculator. Obviously, that's something you need for most designs you do in Australia. But snow and earthquakes exist, not common, but we'd love to hear from you if you do need to do those calculations. I'd love to hear from you if it's worth it for us to build calculators for that. So pop in the chat if you do those calculations.
I just copy and pasted the question as well in the chat.
Yeah, thanks, Addie.
It looks like we've got some responses coming in.
All right, so looks like we've still got a couple of people joining late, so I'm just going to give everyone another minute to get started. But in the meantime, we do have a question for anyone who's just joined. We're trying to decide in ClearCalcs how valuable it would be for us to create snow or earthquake calculators for Australia. So we have a question of how often you actually need to do those calculations.
How does the answers looking like for you, Brooks, so far? Looks like very rarely that.
Yeah, indeed. It looks like one person does it semi-frequently in subalpine regions. Thanks, Andrew. And otherwise pretty rarely for others, if ever. Well, thanks, everyone. Looks like we are settling out with people joining the webinar now, so we'll get started. Today, our webinar is about the Australia and New Zealand's Joint Standard 1170.2, the 2021 revision, which in Australia just became mandatory for all building designs as of about 3 weeks ago, now that NCC 2022 has come into effect. My name is Brooks Smith. and I'll be your presenter for today. So first, a little bit about ClearCalcs. ClearCalcs is a cloud-based design platform to help you design in concrete, steel, cold form steel, or timber, and go through those full design calculations in a clear and transparent manner. So we believe we're more accurate and more precise, both because we have full finite element analysis backing on all of our calculators, allowing you to put your loads and supports wherever you'd like, as well as full test cases based on academic textbooks, design guides, etc., to prove that all of our calculators are accurate and verified. Because we're cloud-based, there's no fighting for licenses with any of your colleagues, so helping to eliminate some wasted time waiting for a license to become available. And we're also available anywhere in the world. So whether you're working from the office, working from home, or even taking us on site on your iPad or whatever. Bit about me. My name is Brooke Smith. I'm the head of engineering research and development here at ClearCalcs. I'm a chartered professional engineer in Australia and a licensed professional engineer in the United States. As you might be able to tell from my accent, I grew up in the United States originally and did my university studies there for both my bachelor's and master's degree. Prior to joining ClearCalcs, I had about 8 years of previous experience in structural engineering R&D consulting. I specialized in cold form steel, and a research fellowship in thin-walled steel, and I was a forensic structural engineer focusing on commercial and industrial structures, mostly made of concrete. I've now been with ClearCalcs just shy of 5 years. I think August is my 5-year anniversary here. So one quick bit of housekeeping. Many of you typed into the chat already, so you know how to access it. But this is where we'd like to ask you to ask any questions that you have along the way. Do feel free to ask them at any time. If it's something quick, I may answer it as I go. But in general, I will save all questions until the end of our webinar and address most questions at the end of the webinar. And also, please send your questions to everyone. Don't send them to just me because I will lose track of them while I'm presenting. So send to everyone so that my colleagues can help me keep track of them as well. So today's agenda, I'm going to give you a high-level overview of the 1170.2 standard, both in how it compares with AS 4055, the residential winds design standard, as well as changes in the new revision of the standard from the 2011 previous version to 2021 version. And then I'm going to go through the general view of the calculations done in 1170.2. I'm not going to go through every single equation, but enough so that you can understand what goes into this and make sure you put in all the correct parameters when you're doing all these calculations. And finally, I'll give you a couple of worked examples using the ClearCalcs platform to determine your wind loads. So first, starting with an overview, comparing with AS 4055, either standard will give you valid wind loads for a house. The difference is that AS 4055 is intended only for residential houses. So only class 1 and 10 structures. Basically, its intention is your house plus the garage or the shed or whatever else. A lot of farm buildings might be covered by it as well. But overall, there's some pretty strict geometry restrictions in addition to must be class 1 or 10 buildings. So those are shown in detail on the bottom here, but essentially building cannot be more than 8.5 meters high, 2-story building. Roof pitch can't be more than 35 degrees. Width has to be less than 16 meters. Length can be whatever you want, but width can't be more than 16 meters. 1170.2, on the other hand, is relevant for most structures you might ever encounter. So everything short of a skyscraper or an offshore oil rig is going to be covered by 1170.2. The big thing that AS 4055 does is it makes a lot of simplifying assumptions. So it's trying to be conservative, but makes a lot of assumptions. 4055 technically is a derived standard. Technically, to write the standard, they go through 1170.2. The committee goes through 1170.2, makes a set of assumptions, and that results in the tables in 4055. So it's entirely based on 1170.2. Key things are that it simplifies about 10 different factors down to one of 10 discrete classes, N1 through N6 and C1 through C4 for non-cyclonic and cyclonic regions. Applies a worst case load in every direction, as opposed to 1170.2, where we look at each direction independently. There are fewer pressure zones. The standard assumes that the average roof height for any building designed in it is 6.5 meters. So if you have a shorter one-story building and you're using 4055, you're actually probably over designing your wind loads, because it assumes that every building has a 6.5 meter average roof height. That's what all these tables are based upon. And simply, it just has 5% added conservatism. Literally, they go through 1170.2 and then add 5% to the wind load, just to make sure that they're conservative. The advantage is that it results in a very simple lookup table. So most of 4055 is based around this one table where you look up which wind class you're part of. And that's most of the standard. So I mentioned coefficients and factors being simpler. There are a lot fewer pressure zones in 4055. We'll talk a little bit more about this later for how it looks in 1170, but there are only 3 roof pressure zones for 4055: corner, edge, and general, or interior of a roof. And you look up a net pressure coefficient in a single table, as opposed to 1170, where you're going to separately calculate the interior wind load and the exterior wind load, and separately consider those. And finally, in 1170.2, there are several K factors that are relevant for different types of elements within a building. You don't really have that in 4055. 4055, you just say, this is the wind load on this part of a building. In 1170.2, K factors can depend upon the total tributary area for your wind beam, and make further adjustments based on tributary area, type of cladding used, a few other factors. And finally, the other big difference, and the one area where 1170.2 is simpler, is that 4055 has a completely independent separate section for calculating total uplift or total racking force. So it is a relatively simple lookup, but it is a separate lookup that makes a lot of conservative assumptions to get you a total racking force. In 1170.2, you just simply take the sum of all your external pressures. So just a simple sum. There are a lot of external pressures you have to sum, but that's all it is. It is just a sum. So now looking at the changes between 2011 and 2021 versions of 1170.2, one of the biggest is that the wind region map has been completely recreated. So whatever you thought your wind region was from 1170.2 2011 or 4055 2011 or 2012, it has may well have changed. So there's now whole new regions. A0, B1 and B2 have been split into separate regions, and New Zealand is now entirely independent wind regions. So A0 is basically the entire interior of Australia. Anything more than 200 kilometers from the coast is A0. And we've also eliminated the special F sub C and F sub D factors for cyclonic regions in Australia. Instead, there's now linear interpolation allowed based upon exactly how far you are from the coast. Leave that to you reference a standard for exactly how to do that. Doesn't make a huge difference, does make some difference. But in short, we removed those special F factors for cyclonic regions. There's also some changes to the multipliers now in 2011. There's a whole new multiplier that's added on to the site wind speed. That's a climate change multiplier, explicitly recognizing the reality that climate change is happening. So the area that I highlighted in purple along the map here, you will be applying a climate change multiplier of 1.05, effectively saying wind speed is going to be 5% higher within the lifespan of a structure that you build in any of those regions. There are a couple of simplifying assumptions now made on the shielding multiplier and hill multiplier as well. Basically just saying that these multipliers are now can be assumed to be irrelevant. If your building height's greater than 25 meters, probably not the case if you're doing residential structures, or if a hill is less than 10 meters in height. So if a feature is less than 10 meters in height, you completely ignore it. We're not going to try and make you calculate every dinky little molehill in the area. And finally, there are some changes to the terrain categories and internal wind factors. So all intermediate terrain categories, except for 2.5, have been removed. And the definitions of the terrain categories have been modified and clarified. The biggest being that terrain category 2.5 is now explicitly for developing outer suburbs. If you're designing in one of the big development complexes in the outskirts of Melbourne or Sydney, you are now terrain category 2.5 pretty explicitly. And I mentioned internal wind factors have some changes, especially if you have large openings in your building. So there's a new open area factor, K sub V, for open structures. It's mostly going to affect things like gazebos, but does affect a bit with like verandas as well. Effectively, it's going to increase slightly the wind pressure on something like a veranda that's a small area, but decrease the wind pressure on, say, a very large gazebo or a concert venue or something like that. And the internal wind pressure coefficients now include area and local cladding factors as well to take into account. Usually this is going to reduce the internal wind load to take into account a bit more accurately how much wind is actually going to make it in through that large opening. So now going into how does the calculation work in 1170.2. So first, a little bit about the overall strategy of the standard. Most calculations in the standard are going to be based upon your average roof height. That's especially for a residential building, anything less than 2 stories. You're basically just going to do everything based on the average roof height. If you had a larger structure, you might separately calculate the windward loads at each individual floor, which would save you some over conservatism. But if you're just designing a residential house, that's usually a waste of time. And just use the average roof height for everything. That can be a little bit tricky to calculate. There's some diagrams in the standard, some more than I copied here as well, showing exactly what average roof height means. If you have a rectangle, it's really easy. It's average of your ridge and your eave height. But if you have anything more complex, it can be a little bit of work to figure out that average roof height. I mentioned one of the key differences with 1170.2 is that we are calculating wind load in every direction independently. So we're going to be looking at site wind speed in each of 8 cardinal directions. So north, northeast, east, southeast, etc. And then we're going to convert those site wind speeds into design wind speeds on each of the 4 surfaces of a building: the front, the right, back, and left of the building. I would note that regardless of the location of your front door, it can be easier in many of these calculations to take the front for purposes of wind calculation to be perpendicular to the long side of the building, or if you have a hip roof, or perpendicular to the ridge of the building if you have a gable or monoslope roof. And just make your life easier for keeping track of what table lookup you use and how you match everything up in 1170.2. Now, I'm not going to, as I mentioned, go through every single formula in 1170.2. If you're doing this by hand, you can look those up yourself. But I want to give you enough information here so that you can use, especially a calculator, accurately and understand what's going on in it. So overall, the entire standard is based around two formulae. So one for the site wind speed, it's going to take into account a base wind speed, directional multiplier, terrain height multiplier, shielding multiplier, topographic multiplier, and I forgot to copy the new version of the standard here, and the climate change multiplier. You'll then convert that into a design wind speed based upon the orientation of your building. And once you have a design wind speed, you need to convert that into a wind pressure to be applied to the actual structural elements of your building. That pressure is based upon the second formula here, where looks relatively simple, although I'd note this shape factor, C sub SHP, is doing a lot of work. It's doing a lot of heavy lifting and includes several different factors within it. To make it a little easier to keep track of, the top of each slide that I'm going to show here is going to highlight the factor that I'm currently considering as I go through this. So for example, you'll see the site wind speed formula on the top of this slide with V sub R, the base wind speed, highlighted in red. So I mentioned this wind region map is entirely updated in 2021 version of the standard here. You are going to select your wind region based upon the location of the structure you are designing. Do note that regions A, B, and NZ are subdivided into different subparts, NZ 1, 2, 3, or 4, A0 through A5, B1, or B2. Once you know the wind region you're in, then you have a couple of table lookups. So based upon the probability of exceedance that you want for your design, and this is defined in NCC 2022, so you don't have a choice on this, then you are going to look up in the table what your base wind speed is, V sub R. For a typical house, which is going to be importance level 2, and either cyclonic or non-cyclonic regions, your ultimate recurrence interval is going to be 500 years, and your service is probably going to be 25 years. Service, you have a little more leeway to decide for yourself what the recurrence interval is going to be. But that's also important. Ultimate and service are considered separately. Have different base wind speeds for those. And then you can just simply look up the directional multiplier in one table that tells you wind in a particular direction, often westerly, is going to be slightly stronger than wind in other directions. Next, you have a terrain/height multiplier, M sub Z. So for this, you need to know your terrain category in each direction. Often the terrain category is going to be the same in every direction, but not always. Say if you're on the edge of a development, maybe it's going to be completely open space in one direction with lots of houses in the other direction. So that does need to be taken into account. If the terrain category varies as you move outwards, then you can average it. And it's taken out to a distance of a maximum of 0.5 kilometer or 40 times your average roof height. And then once you know your terrain category, you just simply look up your multiplier value in a table. Next is shielding. So terrain/height looked at both buildings and vegetation. Shielding is going to look at only buildings. So how many buildings are going to help prevent wind from reaching your structure. Importantly, this is looking within a distance of 20 times the average building height. Now note that terrain category was looking 40 times the average roof height. This is 20 times the average roof height, smaller radius. And you're only going to be looking at buildings that have a height at least equal to your calculation height, your average roof height. And you're going to look independently in each 45-degree arc from your structure in each cardinal direction. Now, one slightly tricky bit here, you have to first calculate a shielding parameter. And one of the factors in that is defined as the quote average spacing, L sub S. Doesn't actually mean average spacing. Do not just simply take an average here. There's an explicit formula. So it's not really average spacing, even though that's the term used to define it. Plug into this formula. If you use a calculator like ClearCalcs, we're going to do this for you, but important to know that average spacing is not actually average spacing. And finally, your topographic multiplier. So this is going to be looking at only the topography around. So you're going to consider features within the closest of 0.5 kilometer or 20 times your average roof height distance. And again, one of the modifications in the new standard revision here is just completely ignore anything that's less than 10 meters in height. So you have a formula based upon exactly the geometric parameters of your hill or escarpment as in a plateau. And for Australia, that's all you need. In Australia, all we care about is the hill shape multiplier. If you are in New Zealand, you do have an additional factor that's relevant in little shaded areas on a map that exists in the standard. I'm not going to go through how that Lee effect multiplier is calculated, but you end up having to combine your hill shape and Lee effect multipliers together if you are in New Zealand. Now, once you have all those multipliers, including your climate change multiplier, then you have your wind speed in 8 cardinal directions in each of your north, northeast, east, etc. directions. But how do you apply that to the building you have? Well, your building has a particular orientation to it. So we're going to take the perpendicular out from each face of your building. So let's say your house is facing a direction of 10 degrees in direction. I'm going to look between north-northwest and north-north and east-northeast for the wind load on the front of my building. I'm going to find the maximum site wind speed within 45 degrees to either direction from the face of my building. And that's going to give me my design wind speed. That's how we simplify 8 directions to 4 directions. So in ClearCalcs, we'll show you 2 different graphs to try and make this clear, showing both ultimate and serviceability wind loads. And you're going to convert that site wind speed in 8 directions to the 4 directions for however your building is oriented. Now, most structures you design, if you're working in a residential world, are going to qualify as permeable structures. There is a 10-page section of 1170.2 that goes through tons of intricacy defining what an opening is and how much opening you need to have or not have to qualify as permeable or impermeable. In general, though, and this is me massively oversimplifying 10 pages into 1 sentence, but in general, anything that can be opened, including doors, windows, ventilators, etc., is going to qualify as an opening for the purpose of this standard. The exception is you can get specially designed doors and windows that are designed to be resistant. So this is not going to be the typical door you go pick up at Bunnings. does have to actually be specially designed to withstand wind loads in whatever region of the country you are in. The vital parameter when you're looking at internal pressures, and this is a hard one for us to even ask about in our calculator because it is a mouthful of a parameter. The ratio of the area of openings on one surface to the sum of the total open areas on every other surface of your building. So this includes your roof. Essentially, it's going to measure how balanced your openings are between different surfaces. If you have the same number and size of windows on every wall of your house or whatever. Just as a dumb example of how this might be calculated, if you have 1 square meter of openings on 3 walls of your building, but 3 square meter opening on 1 wall, then this ratio is going to be equal to 1.0. That's because your maximum opening, 3 square meters, divided by the sum of the other openings, 1 plus 1 plus 1, equals 1.0. So that becomes a 1.0 ratio for the purpose of figuring out what your internal pressure coefficients are here. External pressures, an important point here is just the terminology used. So there's different terminology for walls and roofs. I put it into a table here to try and simplify it a little bit more. So if you're facing the wind, the wall facing the wind is called the windward wall. The roof slope facing the wind is called the upwind slope of the roof. Away from its leeward or downwind, and wind coming from the side, it's your side wall or your crosswind load on the roof. Now, just one particular note here, the wall pressure gets applied to the underside of eaves. So the roof load that you calculate in external pressures is only applied to the top of a roof. To the underside of an eaves, you apply the wall load. So the external pressure is a ton of different table lookups for every direction in roofs or walls. Not going to go through all of those. In general, it's going to give you either 2 values, a minimum and a maximum, or a simple formula. A couple of warnings when you're using these tables. Several of those lookups depend upon some geometry ratios for your building. Depth to breadth or depth to roof height. But which parameter is D and which parameter is B changes based upon the wind direction you're considering. So if you're considering wind that is heading towards the long direction or the long side of your house, then D, the depth, is going to be the short dimension of your house. It's going to be parallel to the wind direction. If you're considering wind that's heading towards the short side of your house, then D is going to be the long dimension of your house. So that changes depending upon which direction of wind you are considering. And also for side and crosswind, there are multiple different pressure zones that you ideally should be considering, up to 4 of them, depending upon the distance from the windward wall or the windward edge of your structure. If you're designing a house, this may not matter that much to you because you may just be making the entire wall exactly the same strength. And in that case, you might just only be looking at the maximum pressure zone. So you as an engineer can make some simplifications of 1170.2 here as you go. But if you want to be really precise, there are lower wind pressures the further you are from the windward edge of your structure. So once you have all those shape coefficients, you have a whole bunch of constants that get considered. So up till now, all of those shape coefficients, everything for site and design wind speeds, you only need to do that once per building. But most of the K factors here depend upon the specific element that you are considering. Element being a beam or a column or a connection or whatever it may be. So these K factors can depend upon which element you are looking at. The main ones here are the volume factor for an open internal pressure, open building internal pressure. This is a new factor in 2021. You have a tributary area factor, a local cladding factor, and a permeable cladding factor, all relevant to your external pressures. And finally, there were also some K sub C values in there. Those are your combination factors. If you're designing a typical house, you may not care about these because you may just be looking at only one wall that's acting semi-independently structurally, for example. But if you're designing a portal frame or something along those lines, these can matter quite a bit. Essentially, this says that all of the wind loads we've calculated up to this point are based upon worst case wind loads. But it's unlikely that you're going to get worst case wind loads on every single surface of your building at exactly the same time. So let's allow you to take a reduction of all of your loads to account for that fact, to account for these probably are not all going to happen worst case simultaneously. There's a giant table, 5.5, in the standard itself that gives you tons of examples with diagrams of exactly what this might mean in real life. But all of it comes down to just 2 sentences in the standard. So it's saying that if 2 surfaces act together in combination, if each surface is going to contribute to the strength you need to consider of the portal frame or whatever it is of the system, then you can take a combination factor of 0.9. If you have 3 or more surfaces acting together, then your combination factor is 0.8. So finally, in ClearCalcs, we try and simplify by putting all of those building parameters together in one calculation that we do for you in our calculator. And then we separately, at the end, apply all these K factors, which can vary by element. Overall, through all of this calculation that you do, you're going to end up with internal and external pressures for 4 different wind directions and 4 different sides of the building. So even for like just looking at your front wall, you have windward loads, you have side loads, and you have leeward loads. So you need to simplify all that down to, well, what's actually the load I'm going to apply when I'm designing this beam or designing this column? Essentially, you're just going to take minimums and maximums. You're just going to take the worst case of all 4 wind directions, and you're going to end up then with 8 values of an internal pressure and 16 values for an external pressure. So 8 for walls, 8 for roof. And now with those 8 plus 16 values, you can finally calculate the actual wind loads on your beam or your column or whatever element you're designing. So you'll end up with usually 2 ultimate loads and 2 service loads. So for example, you might be taking the minimum internal pressure plus the maximum external pressure with all the appropriate K factors applied to it to get 1 ultimate wind load. And then another ultimate wind load is going to be the maximum internal plus the minimum external. Similar for service loads. So you'll typically end up with 4 different wind loads to apply to every individual member. So now I'll go through some worked examples in ClearCalcs. I've got a couple of examples, one for a simple structure where we're going to make an assumption that every parameter is the same in every direction. We're going to do this as simply as possible, but still use 1170.2 instead of 4055. So That's going to be a relatively simple example. It's going to be in Victoria, so non-cyclonic. And then we'll take a directional approach where we're going to pick a site where terrain is very different in every direction. So we will want to customize all the factors in every direction. And this is going to be based in Queensland. So going to have some cyclonic loads relevant there. So let's go through how this is going to look in ClearCalcs. So let me go to clearcalcs.com. If I log in, and I'll use my Google login for my company account. Then our platform is based around the idea of projects. So typically one project is going to be one house or one structure of that, whatever I'm designing, but you can group it however you'd like. So our first example here, let's say example house 1 was at an address in Caulfield North. Now, I just picked random addresses looking at Google Maps. I have no idea whose house this may or may not be. This is just something totally random I picked by looking at Google Maps. But this particular house, well, it's just suburb for kilometers in every direction. So it's pretty flat area right around here. So let's add a wind calculator. We have enough calculators in Australia now that you may want to filter when you are looking to add a wind calculator to get to it quickly. But let's go through some of these parameters. So this is a normal structure. It's not going to be a uninhabitable farm building, and it's not a hospital that has high importance to it. I'm going to design to NCC. That's going to be your usual. It is, in fact, wind region A5. Melbourne is wind region A5. Caulfield North is a suburb of Melbourne. We said that this particular building, the front of it was oriented at about 10 degrees. So just shy of north-northeast. Had a breadth of 14 meters and a depth of 10 meters. So I mentioned that it's a little bit easier to be perpendicular to the long side of the building, to call the front of your building perpendicular to the long side. So usually when you enter this in, your depth is going to be less than your breadth. It's a hip roof and a roof height of 6 meters with a 30-degree roof pitch. Now, that maximum ratio of area of openings, that mouthful of an internal pressure parameter. We're going to assume that's 0.5 with the largest opening on the front. Maybe there's some big lounge room window on the front of the building. Then we go to our terrain properties. So we make it easy for you in ClearCalcs here to, by default, just put in the worst case of all directions. That's going to give you totally valid results. It may be a little over conservative. In this case, it actually probably won't be because every direction pretty much is the same. But this is going to be, in fact, terrain category 3, basically inner suburbs. There are quite a number of shielding buildings. Every building in this region is basically the same size. They're all 1 or 2 story buildings to account for everything with a roughly 6 meter roof height. Let's say I could actually count these up on the map that we show here, but save time here. Let's say that's 15 buildings within that radius. I'll say that they are all going to be just the same height of the building I'm designing, and maybe with a slightly smaller average breadth. Let's be a little conservative here. There are no hills around here, so highest height of hills is just totally irrelevant. And I'm done. That's it. That's all I need to enter here. That gives me all of the relevant parameters for wind. If I wanted to, I could go and customize everything for every individual direction, customize every single one of these parameters. But in this case, I'm not going to. If I want to design for individual elements, we default to showing you some common ones here, but maybe you might want to design a particular wind beam. Okay, maybe it's wind beam 1 and it's going to be on my front wall. I could enter in what are the combination factors here for this. Well, those are probably going to be 1. This is an enclosed building, so my volume factor will be 1. Area reduction factor might be relevant here. I could go through that calculation. Let's just say it's 0.9 here. And local pressures, let's say we do actually have some local cladding that we can take into account here. Maybe this is 1.5 or should be taken into account. And permeable cladding, maybe we do have permeable cladding. So maybe this is 0.9. We are leaving these K factors up to you as the user to calculate, but we'll end up giving you all the relevant values here. Now, at the end of the day, the end results here are going to be a site wind speed, which you'll notice we are calculating for every cardinal direction independently, as well as a design wind speed. Now, why doesn't this design wind speed for ultimate fully match up here? It's because there's actually a hard minimum in NCC saying that the minimum wind speed for ultimate design has to be at least 30 meters per second. So this is taking a minimum of 30. And then we actually have slightly higher on one particular wall of our building, 30.6. Serviceability, on the other hand, has no limitations to it. So on the right side of our building, we actually have very little service load on wind. We'll then have a table of wind loads here, where I mentioned you're usually going to want to end up with 4 wind loads. So ultimate wind load, maximum and minimum, service wind load, maximum and minimum. I added my wind beam 1 on the last row of this table. So that's giving me some particular ultimate and service wind loads for my wind beam here in this right in this table. So this can provide you all of the wind loads necessary for all of your calculations here. So that's our first example. That's a relatively simple one. Everything's the same in every direction. But we can also look at a more complex site. It's giving me a cyclonic region. Everything varies in different directions. So let's look at this example and how that might be entered. Let's create a new project for this because this is going to have a different address associated with it. So example house 2 here. This is, I picked an address of 63 Ellsworth Avenue in Mount Louisa, Queensland. So this is right on the edge of a housing complex with lots of topography in every direction around it, including a nice big hill to the north. So let's add our wind calculator here. Now, this is still going to be a house, so it's still a normal structure, design working life based on NCC. This is going to be, however, in a wind region. I actually forgot to check this before our webinar, but I believe it is B2. I can open up, if I forget to check, I can open up and we now have integrated standards in ClearCalcs. So let's say I want to go check what the map is. I can click on the reference to 1170.2, figure 3.1a. Here is the map for our wind regions. So here I can go see which region is relevant for entering in here. This particular building is aligned so at the front is at 15 degrees. So it's still semi-north facing. The breadth of the building in total is 22 meters. depth of 17 meters, roof height 9 meters. And we are saying that this has a hip roof as well, with a relatively shallow pitch of 15 degrees. So this is going to have a much bigger openings ratio. One particular side of this has multiple doors and a ginormous wall, floor-to-ceiling lounge room window. It's going to be on the front of the building. So I could still make use of the section of this looking at drained properties, worst case in all directions. It might make it a little easier for me to enter in some of this data for worst case initially, because that will then get copied and propagated through as defaults to make my life a little bit easier. So only a couple directions have shielding buildings here, but it looks like they're a little more sparsely spaced. Maybe there are 10 of them within a 45-degree arc. Let's say they're still all basically the same height in the area. That's often true. I do have one hill in the region where the Mount Loiza is 185 meters in height, and the L sub U factor for it is roughly 60 meters. Then the horizontal distance from the crest of that structure is about 250 meters to this building. So I can enter all of that in and then go to my terrain properties in each direction. So terrain category to the north is up down to the south, north, northeast, east, down to the south is still all basically suburb. So terrain category 3 for north through south. But once we start going west, it's more sparsely vegetated scrubland. So that's going to be more like terrain category 2 or 2.5. Let's be conservative and say 2.5. So it's going to update that. Similarly, in those westerly directions, I have no shielding buildings. So let's say 0 shielding buildings in those directions. We'll keep everything else the same for my north through south directions. Hills. I only have hills to the northerly directions, north, northeast, and northwest. So I don't really have any hills to the east through southwest. So let's zero out those. To the west, I have some smaller hills. They're going to be more like 20 meters or so. You may want to spend a bit more time figuring out exactly what these parameters are than I am here. I'm just giving you some demonstration of what you might want to be doing when you are entering in these different parameters. So this is going to go through and figure out all of the hill multipliers in every direction based upon my distance to Mount Loiza and everything else around here. So once I've entered that in, the Lee multiplier is irrelevant, only relevant for New Zealand's here. So that's everything I need. That's going to, again, give me different site wind speeds as well as design wind speeds. Now, this looks fairly different between my site and design wind speeds, and that has to do with the topographic factors that we entered in that amplify some of these site wind speeds in different directions. And again, we end up with our 4 different 2 ultimate and 2 service wind loads to be applied to each of my elements in the building. I'd also just point out while I'm here, if I forget what any of these factors are about, I say L sub U, which is kind of a pain of a factor to calculate. I could click on this reference, and here's my whole section on the hill shape multiplier, including all of my diagrams for, well, what is this L sub U thing? I can go reference this, figure out what it is, figure out how to calculate it, and see the actual standard. This is the most recent version of the standard you are able to see in reference live. If you want to just see the standard, we also have a standards library now as well. So let's say I just want to see the whole 1170.2 standard. I can click into that and then navigate through any section that I'm interested in seeing. Maybe the regional wind speeds. Here's the whole table for regional wind speeds that we're automatically calculating for you in ClearCalcs, but maybe you want to see it yourself. If you aren't sure what standard you want has particular information in it, maybe you want to just search for timber beam and figure out, well, what is the relevant standard for that? We're going to allow you to search within the standards. Maybe timber beam moment, if I want to be really specific. And that's going to tell me, well, maybe Appendix E here is going to tell me some information about the moment for continuously restrained beams. We're still tuning some of our search to make it as helpful as we can, but you can search through all of the NCC standards using ClearCalcs here. For right now, this is available to any new trialist until May 31st. So take a look at that. You can try it out. It will be an additional charge after May 31st. So please check out our website, get.clearcalcs.com/standards, and you can sign up to get early access to our standards as well here. So with that, that is all I have for our presentation today. I'm happy to take any questions along the way. Please enter those into the chat and I will get through what I can with any questions anyone has. So first question here from Callum Hay. Is a hill height you've entered the hill's height above the level that the house is built at, or the height above sea level? Great question. Yeah, it's the hill height is it's actually neither. It's the height of the base of the hill to the crest of the hill. So not from sea level, but from the base of the hill. Now, the standards are written as if every single hill is perfectly smooth and totally idealistic. It's not, so you do have to use some engineering judgment in there, maybe make a conservative assumption as to what the base of the hill actually is. I think Mount Loiza, I think if you take a 30-meter or so base is probably going to be fairly accurate. But yeah, that is the height from base of the feature to the top of the feature. Comment from Tim Messer, the 5% added conservatism doesn't sound right. I think it's the other way around. I'll double check on that. There is an entire appendix to AS 4055 that defines exactly what the assumptions are that they make in deriving AS 4055. So yes, and yeah, Tim, thanks for the clarification. Yeah, case of the does need a high openings ratio, so it's not always relevant. It's only for if you have particularly large openings on one surface relative to other surfaces. Yeah, and openings, as I said, it's like an 8-page section of the standard defining every little intricacy about what is an opening and when. So I am being excessively simple in saying that it's generally anything that can open. But for the most part, and you will be safe if you assume, it is anything that can open. And that looks like it's all the questions for right now. Yes, and Thank you, Tim. Yeah, it's only the windward wall that we care about for very large openings. It's generally not relevant for if it's anything other than the windward wall. Correct. Yeah, I was, as noted, I was not going through every detail of 1170.2. We are at an hour already. I could talk for probably an hour on just how to calculate an internal pressure coefficient. There's a lot of intricacy involved with that, but yes, indeed, good point. Are there any other questions from anyone? Otherwise, I'll stay on the line for another minute or two for any other questions that anyone else has. But that's all we have for our webinar today. We will have a webinar tomorrow specifically talking about our standards integration that is technically still in beta, though fully functional at this point, and will be formally launched and for sale starting May 31st, starting the end of this month. Mark Pasco asks about, could the wind region be linked to the address input? It could indeed, and that is something that we have on our plans for features to add to this calculator. We do want to make this as simple as possible for you. We're well aware of like check wind that exists right now to try and automatically calculate these. We've built most of that capability already in ClearCalcs. We just haven't integrated it yet into this calculator for wind loads. So not only could we automatically link the wind region, but we could also automatically figure out the hill shape multiplier based on the topographic map, automatically figure out your terrain category based on the roughness, and take a reasonable guess at what the shielding factor should be. So we could do all of that automatically. That is something that we do want to and already have much of the capability for adding in the not too distant future. So Addie's posted the link to our Standards Australia webinar for anyone who's interested. Please sign up there if you'd like to know more about our standards integration that I briefly demonstrated in our worked examples here. Tim also asks, in regard to AS 4055, how do you relate it to AS 1170.2? Do they have to be independent or is there a crossover? So in the preface for AS, for both standards, 1170.2 and 4055, they say that you can use either standard, but you must use only one. You can't pick using 1170 for one direction and 4055 for another, or one part of a building versus another. You have to consistently use either one or the other. There is an appendix that I mentioned in AS 4055 that goes through exactly how 4055 is derived from 1170.2. There's one thing I didn't mention and could have here for another aspect of how these relate. In our 1170.2 calculator, let me pick the other one for a better example. We have a field that we give you here of equivalent AS 4055 wind class. This isn't something you can formally use, but it's to help you understand what are these wind loads that I figured out in this much more complex calculation. So this particular calculation I went through for our Queensland location ended up with being equivalent to about N2.9, almost N3 wind class in AS 4055. So we have figured out what that's roughly equivalent to. You can come up with that equivalency. It's not technically something you should be using, but may help be a guidance there. So I don't want to take too strong of an opinion. I don't want to be giving too much specific design guidance on designing a carport. Tim also asked about a carport and using an AS 4055 classification with AS 1170.2. Technically, that's not allowed. Practically, maybe use engineering judgment there. Practically, as long as you as an engineer who's signing off on this are comfortable saying, I have done a conservative calculation, then technically you're doing a performance-based design, but that would potentially be a viable way of doing a performance-based design. So yeah, I don't want to take too strong an opinion on that. That is up to engineering judgment there, but yeah, that may be practical. Mark Pasco asks, how important is the selection of a gable or hip roof type? What is conservative, and what if you have a gable at one end and a hip on the other? So in an ideal world, we don't currently allow this on the ClearCalcs calculator. Please send us a feature request and we'll add your name to the feature request for this if you do want to be able to separately identify different parts as gable or hip. The difference is mostly different lookup tables. And I believe it mostly makes a difference on the crosswind wind loads, for which I think I'm actually gonna need to check this. I don't want to go too much I think with this. But yeah, I'm not actually sure which one is more conservative. It does mostly make a difference with the crosswind wind loads. But you should be able to check the standard relatively easily to just see which is actually more conservative there. Yeah, apologies, I can't give you an immediate answer on that one. Cool. Well, that was a couple of late breaking questions. Yeah, I'll stay for another minute, but thank you everyone for attending. Happy to have this webinar, and always feel free to send us any additional questions you may have to either our email at help@clearcalcs.com or use the help button on the ClearCalcs platform.
And if you have any recommendations for future webinar topics, feel free to add that to the survey that you will be receiving shortly.
Yeah. Thank you everyone for attending.
Thanks everyone. See ya.
Thank you.